Okay, this is 11.2 time dilation. So, this is where relativity is starting to get pretty interesting. Time dilation is the idea that the faster something moves relative to us, the slower it experiences time. And this is true. This is not really, I mean, it has been confirmed. There have been experiments that have shown that this is in fact what happens. So the faster something is moving relative to us, the slower it experiences time. You can think about this in terms of how it was described in 11.0, where we are always moving at the speed of light, and so the more that speed is in the space component, the less it goes through the time component. There are a few other ways to think about it, and in this lesson we're going to be looking at Einstein's original thought experiment that led to this idea of time dilation. So, this thought experiment, we're going to say, imagine someone moving horizontally with speed v, someone moving horizontally with speed v. And they are measuring time with a light clock. So this is going to be a clock that measures time using light. Our light clock here is a device. You can see a picture of it down below right here. That's our light clock. And the way it works is light bounces up and down between two mirrors, taking time delta t equals 2d over c for one cycle. d over c. So we can take a look at this picture of the mirror. You can see that the light moves upward at speed c and back down at speed c, and we have distance is speed over, distance is speed times, I guess, time is distance over speed. So delta t is 2d over c because it's traveling twice this distance between the two mirrors. So you can see our round trip time there is 2d over c. Hopefully that is clear enough that for it to go back and forth it needs to take that much time. Okay, so that's our light clock. We've got somebody who has their light clock on some surface here. So this is our observer 1. He's watching his light clock. He sees the light go up, go back down. It takes delta t to do that. So that's observer 1. Observer 1 is stationary relative to the clock. So from his perspective, delta t, and we're going to call this delta ts for stationary. So the stationary delta t is 2d over c. Observer 2, in this picture, we have an observer somewhere outside watching this person go by. And from their perspective, the light bounces back up and back down, and so it travels the same vertical distance, up and down, but you can see it also travels this horizontal distance, so that after some time, the whole cart here has moved that distance, that means that the light wasn't just bouncing up and down, it sort of followed this path for it to end up there, still on the mirror. Okay, so the light has actually taken a different path here for observer 2. Observer 2 sees the clock moving horizontally, and the light travels the same vertical distance which is 2d, but also a horizontal distance of v delta t. And remember, the light still moves at speed c. It doesn't speed up or slow down, it's still moving at the same speed, but now it has a longer distance to travel. If it's moving the same speed, further distance, that means it must be taking more time to do that. Which is the whole result here, that it's taking more time from observer 2's perspective than observer 1's perspective. It means that time seems to be moving slower in observer 1's frame than in observer 2's. So, we have an equation for this. We can say that delta Tm, which is the time from the moving frame of reference, so from observer 2's frame of reference, because observer 2 is moving relative to the clock, or the clock is moving relative to the observer. Okay, so delta Tm is equal to delta Ts, the stationary time, over the square root of 1 minus v squared over c squared. And the whole derivation for that is in your textbook if you want to check it out. It's a cool derivation. But there it is. There's our relationship. So from the observer 2's perspective, the time seems to take this longer amount, delta Ts over root 1 minus v squared over c squared. So you can see that this bottom term here, the largest this bottom term can be is, well, this is going to be less than or equal to 1. Because v squared over c squared, we're always going to be subtracting that from 1. So that bottom term is less than or equal to 1. Which means that this ratio is always going to be at least 1. Okay, so proper time is what we call delta Ts. Delta Ts is the time that the stationary observer was measuring. So the one that wasn't moving relative to the clock. So delta Ts, which is the time measured by an observer at rest relative to a clock. And delta Ts is less than or equal to delta Tm always. Okay, there's our relationship. We have an equation for delta Tm, and we're going to do a problem on the next page. You can see there's a little graph here showing delta Tm over delta Ts. You can see that when v over c is 0, so when the clock isn't moving at all, you can see that the ratio here is 1. You can see that as the clock is moving faster and faster and faster relative to the second observer, our ratio goes up and up, where it approaches infinity as the clock approaches the speed of light. Alright, so on this next page here, we have on Earth, an astronaut has a pulse of 75.0 beats per minute. He travels into space in a spacecraft capable of reaching very high speeds. Determine the astronaut's pulse with respect to a clock on Earth when the spacecraft travels at a speed of 0.10. Okay, so we can use our equation for this. We have delta, delta t m is equal to delta ts over root 1 minus v squared over c squared. So to get my delta t, first I'm going to convert 75 beats per minute into the period for 1 beat. So I'm going to say here delta ts is equal to 1 over we'll just say 1 over 75, and we're going to get a value here of 1.34 times 10 to the negative 2 minutes. I didn't convert it into seconds because we're going to convert this back in just a minute anyway. So 1.34 times 10 to the negative 2 minutes. That's our delta ts. Okay, so I can get my delta tm here is equal to 1.34 times 10 to the negative 2 minutes over square root of 1 minus v squared over c squared. Well, we have, basically this is going to be, well, I'll do this here, 0.10 c squared over c squared. And you can see that the c's are going to cancel out here, so we get c squared over c squared. So we get 1.34 times 10 to the negative 2 over root 1 minus 0.01. And this gives us a value of, 1 second here. I'm sorry, I did make a bit of a mistake here. So delta ts was 1.33 here. 1.33, which means that here I also need to have used 1.33, and here 1.33. 1.33, 1.33, and that gives us an answer of 1.34 times 10 to the negative 2. So, sorry about that mistake here. So that's how many minutes it takes for 1 beat. And now we can get the pulse again. So pulse, you can see this, the delta t has changed a bit. So we're going to get the pulse is going to be 1 over delta tm. So 1 over 1.34 times 10 to the negative 2, which is equal to, that's equal to 74.6 beats per minute. So you can see that it's a bit slower, but it's still, that's approximately 75 if we're using our sig figs. Okay, now we'll do the exact same thing for part B. Determine the astronaut's pulse with respect to a clock on Earth when the spacecraft travels at a speed of 0.90 c. So we just looked at 0.1 of the speed of light, now we're looking at 0.9 of the speed of light. Same idea. We have delta tm is equal to delta ts over root 1 minus v squared over c squared. And we had our delta ts from the last part, 1.33 times 10 to the negative 2 minutes over square root of 1 minus 0.9 squared, or 0.9 c squared, I'll fix that there. 0.9 c squared over c squared. And of course the c squareds cancel out, so we get 1.33 times 10 to the negative 2 over the square root of 1 minus, so 0.9 squared is going to be 0.81. And this gives us a result of delta Tm equals 3.05 times 10 to the minus 2 minutes. Okay, so you can see now from 1.33 to 3.05, we've more than doubled the duration of the pulse. So now we need to get the frequency of the pulse. It's going to be 1 over delta Tm, 1 over 3.05 times 10 to the negative 2. This is equal to 33 beats per minute. So you can see now at 0.9 of the speed of light, this astronaut's pulse has changed quite a bit. Okay, so that's how we do these sorts of problems. There was the added sort of trickiness with this of having to take the reciprocal to go from frequency to period, because delta Tm had to work with a time measure of period. Alright, so that's time dilation. It's a very real thing that does exist. We can measure it. It happens all the time. One of the places where you do notice it is things like half-life. So we have particles that have a certain half-life. We know that they decay at a certain rate. And if we take those sorts of particles and send them at very high speeds, we'll see that they decay slower relative to us than they should normally, because they're experiencing time at a slower speed than we are. And so it is something that is very measurable and has been confirmed. Now, along with this whole idea is the concept of the twin paradox. And in your textbook, the twin paradox is covered in the next lesson. We're going to cover it here instead, because I thought it goes well with this lesson, because it's all about time dilation. So our twin paradox, imagine two rockets, or sorry, imagine two twins, sorry. Twin 1 leaves Earth in a high-speed rocket, then returns home, and what does he find when he returns home? Finding that twin 2 has aged more than twin 1. Okay, so this is the twin paradox. That is what would happen if a twin jumped in a high-speed rocket and flew away from Earth and then came back. Well, everybody on Earth would have aged more than this person in the spaceship would have. And at first that makes sense, because you say, oh, time dilation. Well, he experiences time more slowly than we do. But I'm going to say here, why does this happen? Sure, it seems like time dilation should explain it, but actually, for both twins, time should seem slowed down for the other twin. So the one that's hopped in the spaceship, from his perspective, he's not moving at all, and everything else is moving around him. So he flies away from Earth, which means that the Earth flies away from him, and then Earth flies back towards him. So his twin back on Earth was moving at this relativistic speed. He was experiencing time slower than the twin in the spaceship. So it doesn't seem to make sense, because really, from both perspectives, time should have been slowed down for the other person, and it shouldn't really work. There's two ways of viewing the solution to this. Solution 1. This is using what I talked about in lesson 11.0, the idea that we're always moving at the speed of c through space and time. So solution 1, for paths from A to B, the shortest path through space is also the longest path through time. For paths from A to B, the shortest path through space is also the longest path through time. So if I'm here sitting on Earth, and I'm not really doing much to leave Earth, I'm staying here. Now, Earth isn't a perfectly inertial frame either. It's rotating, it's accelerating in a slight bit, but mostly we're just sort of, we're not accelerating too much on Earth. And this is sort of an important idea, that we are basically in an inertial frame that is not accelerating here on Earth. The person who jumps in their spaceship and drives away and comes back, well, they're taking a much longer path to go from point A to point B through space. So that means that they must be going less through time. Okay, so that's one way of looking at this. And again, it gets into some trickiness of saying, well, is it really a shorter path, what we're experiencing on Earth? Who's to say that that's shorter? And again, it's sort of relative. So solution 2 is maybe a better way of looking at it. So let's see. When twin 1 changes direction, so twin 1 is the one on the spaceship. When twin 1 changes direction to come back home, he switches between two inertial frames. Two different inertial frames that line up differently. With twin 2. So we can say twin 1 is driving away in an inertial frame, away from Earth, and then he drives back towards Earth in an inertial frame. But at some point, those two frames are different. At some point, he had to accelerate to change directions. He had to switch inertial frames. And that switch is what causes this mismatch in their time alignment. So you can see the picture to the right here of what's happening. So we have the stationary twin is just going straight here, not moving from their perspective. And the other person is going away and then coming back. Okay, and so going away and coming back, even though going away is an inertial frame and coming back is inertial, that switch here is where things get sort of changed. So you can see we have these lines where time lines up. So we can say that the stationary twin here at that point in time lines up with this point in time for the moving twin. That point in time lines up with this point in time. That lines up with this. Then when we switch inertial frames, now those two times are lined up in this other location. So that at that change, there's a large span of time that's sort of all of a sudden gapped, bridged over. Okay, so that's what's going on. That's why things don't line up, is because we're not staying in one inertial frame. Now, for the twin that's driving away from Earth to stay in a single inertial frame, they'd have to keep on going away from Earth, and they could never come back. Okay. Now, this whole situation has been verified. Time dilation has been verified. The twin paradox has been verified in the 1970s. Time dilation was verified. using atomic clocks on passenger jets. Atomic clocks are clocks based off of the decay rate of some radioactive substance, and they put these clocks onto passenger jets that flew around the Earth a couple of times in opposite directions, and also they compared that to one that was sitting on Earth, and took into account all the, different effects going on, but they did find that the time on these clocks ended up being mismatched by a very measurable amount. It's been replicated over and over again. This is definitely something that happens in the real world. So it's a pretty cool phenomenon. Give those homework problems a try, and we'll see you in the next lesson.